Here we're going to continue our discussion about phase equilibria. In particular, we're going to consider the detailed thermodynamics of Raoult's law. If you remember from last lecture, we decided to study phase equilibria, and we said that typically what one does is make a pressure-temperature diagram and put on points of interest like a critical point, triple point, solid, liquid, and gas. And we considered that in detail for a single component. And we said for a single component, a single pure substance, we have 2 degrees of freedom. And we generalize this to the Gibbs phase rule, where the degrees of freedom is equal to the number of components minus the number of phases that you want to be in phase equilibrium plus 2. And then for a single component, for C is equal to 1, and you want any phase, it doesn't have to be any phase equilibria. This implies that your degrees of freedom was equal to 2, and we said the 2 degrees of freedom are temperature and pressure. We can independently specify temperature and pressure, and once we specify those, then we know what the phase is. So phase equal 1. If, on the other hand, we have a single component, and we want the number of phases to be equal to 2, for instance, liquid and solid to coexist, that means that degrees of freedom equals 1, and so on. Well, now in this lecture, what we're going to consider are 2-component systems, where you have just not a single pure substance, but now you have 2 components. Well, the degrees of freedom for this system are the number of components, which is 2, the number of phases. Let's take in general, we have 2 phases that, 2 phases that can exist anywhere. We have 4 minus the number of phases. So if we just want a single phase, we're not going to put any phase restrictions, then the degrees of freedom will be 3. So here we have 2 degrees of freedom. This is the X and Y axis. Now with 2 components and no phase equilibria, which means that the number of phases can be equal to 1, so we have no constraints, then the degrees of freedom will equal 3. So really what we need is a 3-dimensional graph. So along one axis will be pressure, along the other axis will be temperature, but that third axis, this will be, say, mole fraction of the first component, or it could be mole fraction of the second component. You don't need a 4th axis because the mole fraction of the 2 components have to sum to 1. So in general, for 2 components, we need a 3-dimensional graph. So typically what one does is to plot it at constant temperature, which corresponds to planes intersecting the temperature axis. And therefore you have a 2-dimensional graph, pressure versus composition. And usually it's the mole fraction of, or you can have constant pressure that corresponds to planes across intersecting at right angles with the pressure axis. In that case, you would plot temperature versus composition. So you have pressure composition or temperature composition. Now for the first part of this considerations where you have 2 components, we'll consider pressure composition graphs. So in general, that's what we'll have. We'll just have slices in this 3-dimensional graph where you have 3 degrees of freedom. We'll restrain one of the degrees of freedom. We'll get rid of it by saying constant temperature, pressure, and therefore you have these 2 graphs. Now, if we want to put in a phase equilibrium, typically 1 and 2 here, the subscripts 1 and 2, represent the 2 components. And this is the chemical potential in phase 1 of component 1 will equal the chemical potential of component 1 in phase 2, and a similar expression for component 2. So now these are constraints, and if we put these constraints in equilibrium for phase diagrams, we're going to reduce the degrees of freedom. Let's see in more detail what we're talking about here. Suppose we have a sealed system here, and let's take a single component, and this will be a liquid. So here we have a single component. We'll denote that with the 1, which we're eventually going to put as a subscript. And this will be in the liquid phase. But as we know, at equilibrium, the liquid will be in equilibrium with the vapor. It'll have a certain vapor pressure. Liquids usually have vapor pressure in the gas phase. So if we want phase equilibrium for a single system, remember we're going to reduce our degrees of freedom by 1. So instead of a two-dimensional plane, we now have just a single line we have to follow. We said that the chemical potential of component 1 in the liquid phase at phase equilibrium has to equal the chemical potential of component 1 in the gas phase. This is at phase equilibrium. All right, now let's develop this. Let's look at thermodynamically in more detail what's happening here. We're just looking at the single component, and then once we understand that, we'll add another component here. The chemical potential of component 1 in the liquid phase will be the chemical potential of component 1 in the liquid phase, standard state, plus RT times the natural log of the activity of component 1 in the liquid phase. The same way with component 1 in the gas phase, that's equal to the chemical potential of component 1 in the gas phase, standard state, plus RT times the natural log of the activity of component 1 in the gas phase. All right, now as we said, for condensed phases such as water liquid or water solid, for solids and liquids, the activity of the condensed phase, which we have, if we're just looking at the liquid, that's a condensed phase, and we have a single component, so it's pure. The activity of the liquid phase, in this particular case, we have a single component, will be equal to 1. And the activity of the gas phase, remember the activity, let's say of component 1, the gas phase, that will be equal to the pressure in the gas phase divided by the pressure at some standard state times some fugacity constant for the first one. Let's assume that we have an ideal solution so that this is just the pressure of component 1 divided by the P0. That's what the activity is. And let us denote further that the substance, we'll put a star up there. That star means that we're doing a single component, and the single component is pure, so this will be the vapor pressure of the pure component above the solution. So that's what that is. Vapor pressure of the pure component. That's what that star means there. So we have an expression for the chemical potential in the liquid, the chemical potential in the gas phase, and at phase equilibrium, the chemical potentials are equal. So with that, let's equate these two. At equilibrium, they're equal. So on the next page here, we'll equate those two. So the chemical potential of liquid is the chemical potential of liquid in the standard state. So you note that this term goes to 0. So the chemical potential of liquid is the chemical potential of standard state. Well, that sort of makes sense because it's a pure substance. And so that is equal to the chemical potential in the gas phase. If this is component 1 in the liquid phase, component 1 in the gas phase, standard state, plus RT times the natural log of the vapor pressure of the pure substance divided by the standard state pressure. All right, that's interesting. It relates the chemical potential of the liquid, standard state chemical potential liquid, to the standard state in the gas, plus this sort of correction term because you don't have the vapor pressure above the liquid to be equal to the standard state 1 atmosphere usually. So remember that equation, that'll come in handy a little bit later.